Welcome to the fundamental crossroad of inferential statistics, choosing between the z-test and the t-test. In the world of data science and research, making the wrong choice can lead to misleading p-values and incorrect conclusions. Today, we will master the criteria to distinguish them, ensuring your hypothesis testing is always robust and mathematically sound. To understand these tests, we must first revisit the central limit theorem. This theorem states that as a sample size grows, the distribution of the sample means tends towards a normal distribution, regardless of the population's original shape. Both the z-test and the t-test rely on this bell curve logic, but they differ in how they estimate the variability of that curve. Let's start with the z-test. The z-test is the gold standard for large data sets. Historically, we use a z-test when two conditions are met. First, the sample size n is large, typically greater than 30. Second, and most importantly, the population standard deviation, denoted as sigma, must be known. In modern big data scenarios, such as analyzing millions of transactions at a company like Amazon or Google, the z-test is highly reliable because the sheer volume of data makes our estimates of variance extremely precise. Now meet the student's t-test. This test was developed by William Seeley Gossett in 1908 while he was working for the Guinness Brewery. Because he was dealing with small batches of beer, he couldn't rely on the z-test. The t-test is used when the sample size is small, usually less than 30, or when the population standard deviation is unknown, which is the case in almost all real-world scientific research. Instead of sigma, we use the sample standard deviation, S, to estimate the spread. Visually, the difference lies in the tails of the distribution. A t-distribution is shorter and has thicker tails than the standard normal z-distribution. This is because with smaller samples, there is more uncertainty and we need to be more conservative. As the sample size increases, the t-distribution starts to morph. When the sample size reaches infinity, the t-distribution becomes identical to the z-distribution. Let's look at a practical flowchart for your decision-making. Step 1. Is the population variance known? If yes, and the data is normally distributed or n is large, use the z-test. Step 2. If the population variance is unknown, which is common, check your sample size. For n greater than 30, the z-test is often used as an approximation, but the t-test is technically more accurate. For n less than 30, the t-test is mandatory. Consider two real-world examples. Imagine a light bulb factory that has produced billions of bulbs. They know exactly that the population standard deviation of bulb life is 50 hours. To test a new batch, they use a z-test. Now imagine a medical trial for a rare disease with only 12 patients. The researchers don't know the population's variance, so they must use a t-test to account for the high uncertainty of such a small group. In summary, use the z-test for large samples with known population variance, and use the t-test for smaller samples or when you only have the sample variance. Mastering this distinction is the first step toward becoming a truly data-driven professional. References: 1. Moore, D.S., McCabe, G.P., Craig, B.A., Introduction to the Practice of Statistics. 2. Gujarati, D.N., Basic Econometrics. 3. Student, W.S. Gossett, The Probable Error of a Mean, Biometrica, 1908.